Alright then, hello everyone and welcome to my Logic Design with Verilog course. In this section of the course we're going to be going over combinational logic in Verilog. And now I do expect you to have some sort of knowledge of digital logic. If you don't, I have uploaded a video series on digital logic if you want to give that a read through. So without further ado, basic constructs. Verilog is a hardware description language, or HDL, that is used to model, design, and simulate digital circuits. It has constructs similar to programming languages, but its focus is on describing hardware behavior and structure. Modules are fundamental building blocks in Verilog. They encapsulate a circuit with inputs, outputs, and internal logic. They have the file extension .v. So this is the basic layout for, say, an AND gate. So we have our output Y, and by design, outputs usually come first. Then we have our input A and B, and then we use the assign keyword to assign the output Y equal to A and B, and we end the module. And down here, this is how we write comments. Data types and operators. Nets, or wires, represent physical connections and must be driven continuously, like right here. And then registers store values until they are explicitly changed. They are used in procedural blocks like always in register queue. We will use always, we will go over always blocks in the next lecture. Vectors are for multi-bit wires and registers. So here we have wire, that's an 8-bit bus called data. Parameters are constants for reusability, so they're kind of like variables in Verilog. And here are some operators where we have our basic arithmetic operators, our bitwise operators, our logical operators, relational operators. So, you know, if you've done any programming before, none of this really should be new to you. But we also have concatenation and replication operators as well that we'll use in later as examples. Expressing numbers using different bases. So the syntax for specifying the base of a number is as follows: the size in bits and the base and value. So basically you'll use this notation a lot. So if you want to declare a 4-bit number, you would do it this way. And if you want to let's see, and then an 8-bit number, so if you want to declare a number in hex as well, you would use this notation. And then you would get this value in binary. So you get the basic idea. Modules. So a module in Verilog is like a blueprint for a piece of hardware. It describes the interface with the inputs, outputs, and in-outs, the internal logic, combinational, sequential, or structural, and how it connects to other modules. Think of it like a function in software, but instead of running code, it describes an actual circuit. And this, again, this is how we declare a module. So it's module name in the port list, with the port declarations down here, the internal signals, and the logic of what we want to do. So some examples. We would use, this is how we would make an AND gate with the output Y, input A and B, and we assign Y equal to A and B. A multi-bit adder. So if we wanted the output to be a 4-bit vector called sum, an input vector, a 4-bit input vector, and then another 4-bit input vector, and then we assign sum equal to A plus B. Notice that there is one more bit here, just in case of any carry. So it's a 5-bit sum. Module initiation. Modules can be reused by initiating them inside other modules. So consider the module top, where we declare wires A, B, and Y, and we use the AND gate from above, and then we declare the instance name U1, and then we map the port inside the module to the signal. So it looks like I have a bit of a typo here. It should be, Y should be over here because that's the calling order. Alright, continuous assignments. In Verilog, we use continuous assignments to model combinational logic. They are declared using the assign keyword. They continuously drive a wire, a not register, whenever a signal on the right-hand side changes. The assignment is automatically updated. So again, module AND gate output Y, input A, B, and then sign. So the sign statement continuously drives y. So if A or B ever changes, y updates immediately. Verilog allows all logic operators. So for in this module, we have the output y1, 2, and 3, and input A, B, C. So for this is what we would do for bitwise AND, or bitwise OR, and then logical NOT. So this module simple gates without writing always blocks. Continuous assignments continued. We also use the conditional ternary operator where we can model multiplexers. So in this module, if cell, so if cell is 1, then B, else, then A. You can see down here. And the example below uses the conditional operators. So we assign 1 based on this truth table. So whenever we have 1, 1, 0, we assign 1. Or if we have 1 and 1 and 1, we assign 1. And what else if we ever have 1 and 1 and 0, we also assign 1. Any other times we assign 0. So we can also use delays in simulation only. So we can say in the module delay example, so we say y updates 5 time units after A or B changes. Structural design. In general form, this is a module name with the instance name, dot port name, signal name, dot port name, signal name. So this is how we would initiate multiple modules where 2 input and gate is feeding into an OR gate. So we declare the OR gate here, and then we also declare the AND gate over here. So in the top level structural design, module top is output, for output Y, input A, B, C. We declare a wire.1. So first we initiate the AND gate, and we send wire 1 in here, A and B. And then for the OR gate, we send the updated values of Y, W1, and C. Gate level primitives. The basic logic gates in Verilog include AND, OR, NAND, NOR, XOR, XNOR, and NOT. Example. So in this gate example, we use AND G1, where we get T1 equal to A and B, or G2, where Y will be equal to T1 or C. A user-defined primitive. A user-defined primitive is a truth table definition of a logic function. It behaves like a built-in gate primitive, but is defined by the designer. It can be a combinational UDP where the output depends only on current inputs, and a sequential UDP where the output depends on current inputs in previous state, like latches or flip-flops. So this is the basic way you would do it. So you would use the keyword primitive name, input 1, input 2, and then the output out, input in 1 and 2, and the register out, needed for sequential UDPs. And then this is how we would declare the table. We use the question mark for don't care scenarios. So in this example, for a 2 import XOR, we import the truth table for an XOR, so it's only true when we either have A or B equal to 1. And we use the keyword primitive, and then out A, B. Test benches. A Verilog test bench is a separate module written only for simulation. It simulates the device under test, or DUT, with inputs and monitors the outputs. So here, for example, we have a 2-to-1 multiplexer, where we just say the output 1, input A, B, cell, so assign Y equal to, if cell is true, then B, else A. So this is how we'd make the test bench. We don't use any inputs or outputs. So we declare our registers A, B, cell, and then wire W. We initiate the device under test. So A goes into A, B goes into B, cell goes into cell, and Y goes into the output Y. Okay, again, this should be over here, another typo. I'll fix that on when I upload these slides. So initial begin. We initialize our variables all to 0, and we apply our test vectors. So after 10 seconds, a equal to 1 and cell equals 0, we expect the output y to be 1. Then after another 10 seconds, we set b equal to 1, cell equal to 1, and we expect the output to be 1. Then finally, a equal to 0, b equal to 1, and cell equal to 0. We expect y to be equal to 0. And then we end the simulation using the $finish keyword. And then we use the monitor keyword to continuously print whenever any listed signal changes. So at t equal to 0, and then over here. So this is the conclusion of this lecture. In the next one, we're going to go over Verilog for sequential logic.